Hello everyone. Last class we covered student workbook problems. Now let us see classroom workbook problems. Let us see student workbook problems. Okay. Let me give what are we covering now. Our subject is analog circuits. And we are doing chapter 2, BJT amplifiers. Student workbook problems. Right? Now let's see problem number 1. Please check the problem number 1 from your side. Let me read it out. In the cascade amplifier shown in figure, if the common emitter stage has a transconductance GM1 and the common base stage has a transconductance GM2, then the overall transconductance of the cascade amplifier is. Okay. Let me draw the circuit. The circuit is this is your VI. This is transistor 2, transistor 1, and this is what is the load. This is RL, this is what is your V0, okay, and this is what is your I0. Okay, what is he saying? Actually this is what is your input and this is what is your output. Now what is asking is the transistor Q1 is having transconductance of GM, therefore your transistor Q1 is having transconductance GM1 and transistor Q2 is having transconductance GM2. Then he is asking overall transconductance. When I say overall transconductance, this is what, if I say this is what is your circuit or this is what is your amplifier, it is a black box for you. You are giving your input signal and you are taking your output signal here. Now for this combined circuit, what is transconductance? Therefore this is what is your amplifier. Remember, this is what is your cascade amplifier. Why it is cascade amplifier? It is not cascade. Why it is not cascade? I'll tell you. Let me tell you. What do you mean by cascade amplifier? If you take, let us say this is what is multi-stage common emitter amplifier. Let us say this is what is your CE amplifier, and the output of CE amplifier, if you are giving it to one more CE amplifier, right? And this is what is your input and this is what is your output. Basically this is nothing but your multi-stage amplifier, right? If you have similar type of configuration, right, then this is what is stage 1 and this is what is stage 2, and stage 1 is common emitter amplifier, the same configuration in stage 2, and this is what is called cascade amplifier because they are in cascade section. This is what is cascade amplifier. Okay, if the first stage is common emitter amplifier and the second stage is common base amplifier, these two are different combinations are different configurations, then that is not called as cascade amplifier. That is the terminology people followed, and that will be cascode amplifier. Therefore, whatever he told in the problem statement saying that this is cascode amplifier, let me tell you how it is cascode amplifier. Basically, this is AC circuit. Okay, no biasing is shown. Now, tell me for your transistor Q1, this is collector, this is emitter, and this is base. Right? Now, similarly for transistor Q2, this is what is our emitter, base, and collector. Therefore, tell me if I say this is what is stage 1 for transistor Q1 and this is what is stage 2 for transistor Q2, then tell me for Q1 we are applying input voltage at the base with respect to ground, emitter is at ground, we are taking output voltage at the collector with respect to ground, emitter is at ground. For both input and output, emitter is common. If emitter is common, this is what is common emitter configuration. Therefore, this is common emitter configuration. This is what is CE. Now, output of CE, you are giving it to transistor 2. Now, let's see what is this configuration. We are applying output of first stage, which is nothing but input to second stage. We are applying input at the emitter with respect to ground. Ground is nothing but your base. Taking output at collector with respect to ground. Again, ground is nothing but your base. For both input and output of second stage, base is common. Therefore, this configuration, this is what is your common base configuration. Therefore, now tell me, common emitter configuration output is given to common base amplifier. Therefore, it is CE-CB combination. If it is CE-CB combination, let us say this is what is our CE amplifier and this is what is your CB amplifier. Then this is your output and this is your input. This is what is called cascode amplifier. This is what is your cascode amplifier. Two different configurations where we use CE amplifier and then CB amplifier. This is what is called cascode amplifier. Now, the next question, what is the difference between cascade amplifier and the cascode amplifier? You try to write, then we'll continue. Did you write this? After writing this, I'll explain what is the difference between cascade and the cascode. What is the reason people are taking for two different configurations? Actually, indirectly we had seen this. You remember we studied common emitter amplifier separately, common collector amplifier separately, common base amplifier separately, and we had a conclusion. What was that? Common emitter amplifier is providing very good voltage gain, very good current gain, but there is no impedance matching for voltage amplification as well as current amplification. CC amplifier is giving very good impedance matching for voltage amplification, but there is no voltage gain. CB amplifier is providing very good impedance matching for current amplification, but there is no current gain. Then what we did? We combined CE amplifier with CC amplifier. CE and then CC. CC will be at the input stage and CC will be at the output stage. Two CC amplifiers at input and output. One CE or two stages of CE or multi-stage configurations of CE in the middle. Therefore, this is what is completely different configuration, but overall we are achieving something. Similarly, if you want current amplifier, first stage will be CB amplifier, the last stage will be CB amplifier, and the middle stage will be CE amplifier. Therefore, this will give you, the CE amplifier will give you current gain, and CB amplifier at the input as well as output will give you impedance matching for current amplification. Therefore, overall it will become a current amplifier. Similarly, therefore this is CE amplifier and CB amplifier. Okay. See, from cascade amplifier also, whatever voltage gain, let us say this is having voltage gain AV1 and this is having voltage gain AV2, then overall voltage gain, if you ask me overall voltage gain, it will be AV1, approximately AV1 into AV2. If I neglect loading effect and source effect. Then if you take cascade amplifier, the first stage, let us say AV1, tell me common base amplifier is having current gain 1, but it has voltage gain. The voltage gain is approximately the first stage is AV1 and common base amplifier is also having gain of significant gain, let us say AV2, then your overall gain will be again close to AV1 and AV2. Then what is the advantage of cascade amplifier with respect to cascade? See, in the case of cascade amplifier, similar configurations, your gain, overall gain is, which is nothing but AV1 into AV2. Similarly here AV1 into AV2, right? Overall gain was fine. But remember here, we are like, this is what is having GM1, this is also having some GM, therefore we are multiplying GM and then it is having some R01, this is what is R02. Without impacting your R0 by increasing GM, like GM into GM, that is what we are getting indirectly overall. But here, even though individually like cascade, CE amplifier, CB amplifier, individually you are seeing, but overall if you see the combination of circuit, that is what it is. Now, it will have GM won't be affected, that is what we need to see, that is what is asking. For the combined amplifier, what is your trans conductance? Then only your R0 will be affected, because what is your voltage gain? If you consider hybrid pi model of your BJT, your voltage gain is minus GM into R0 for common emitter amplifier. Therefore, for common emitter amplifier, indirectly can I say this is the load for your CE amplifier? I am speaking with respect to combined amplifier, not like separate, right? That is to explain with respect to cascade amplifier. Therefore, if I take the combination and then let's see what is that. For your Q1, your Q2 is nothing but what? Indirectly the load resistor, and this is what your actual AC load, what it may be. Therefore, now you know if this is not there, actual load will be your load for Q1, but because of this there is extra resistance, that resistance is increasing because AV is equal to minus GM into load, indirectly the effective load is increased due to Q2, therefore overall gain will be increased. Okay, that is the concept. Maybe when you go to higher education, you will see all those things in detail. But currently, the problem is, just I gave you a little introduction about the cascade amplifier. But remember, without impacting, without increasing GM, only by increasing R0, then this is what is going to give you, bandwidth won't be affected actually. Okay, those things we will see later. Now, the question is, this is what is having GM1, this is what is having GM2, then what is our overall transfer function? Right? First of all, what is GM? We know that GM is nothing but change in output current with respect to change in input voltage when your output voltage is constant, right? That is what. Therefore, what is transconductance? Whether it is BJT, JFET, MOSFET, any device, any block, GM is defined as what is change in output current with respect to change in input voltage when output voltage is constant. This I already defined. Okay, this is what is for. Then what is GM1? Therefore, what is GM1? GM1 is nothing but change in output current, which is nothing but IC1 with respect to change in input voltage, which is nothing but VBE1 when VCE1 is constant. Right? Then what is GM2? GM2 is nothing but change in output current IC2 with respect to change in VBE2 when VCE2 is constant. This is what it is. Okay. Now, if you listen carefully, right? Now tell me what is GM, overall GM. Therefore, what is change in output current? Your change in output current is nothing but change in collector current of your Q2. Therefore, can I write it as change in output current, which is nothing but IC2 divided by what is change in VI? VI is nothing but your first transistor VBE. Change in VBE1 when your total output voltage, that is what your V0, that is what is constant. If you apply KV, what is V0? This voltage is equal to, this is what we are applying, right? VCE2 plus VCE1, right? Let us say VCE1 and then VCE2, if you take V0 constant, approximately VCE1 is also constant, whatever it may be. Tell me what is ICE2? We know that if you observe clearly, this is nothing but what? This is what your current, this is what your IC2, right? Collector current, the same current, because if I neglect base current, if beta is very large, your IC is approximately equal to IE. The same current is nothing but what? This is nothing but your IC1. Therefore, can I say your IC2 is approximately equal to IC1? Your IC2 is approximately equal to IC1. If IC2 is equal to IC1 approximately, then dou IC1 divided by dou VBE1. If I say output voltage constant, let us say your VCE1 is also constant. Then tell me what is this? Change in collector current of transistor 1 to change in emitter voltage, base to emitter voltage of transistor 1 when VCE1 is constant, that is nothing but your GM1. Therefore, this is approximately GM1. This is what is the answer. Therefore, what are all the options we have? I think option A, GM1, option B, GM2, option C, GM1 by 2, option D, GM2 by 2. Therefore, tell me what is the answer? Answer is GM1. Yeah. Take it. We will see problem number 2. Now I can give you one point. Actually, if you compare cascade amplifier to cascode amplifier, your overall gain is almost same. Your cascade amplifier and then cascode amplifier both are having almost same voltage gain. Your voltage gain is improved from single stage amplifier. But people practically use cascode amplifier. Reason is, if you compare these two, right, this will have more bandwidth. This will have more bandwidth than this. Because we have individual stages of CA amplifier and CE amplifier, then we have like GM1 R01, GM2 R02, the parasitic capacitances which are coming to like C1 and AV1 and A2, AV2 are more. If you have more cap, it will limit your bandwidth. But coming to cascode, let us say that therefore indirectly the output of that is given directly to emitter, therefore there is nothing in between, therefore directly we can reduce what we call the parasitic capacitances, then we will see that. This is like with respect to hybrid pi model, if you solve the transfer function of this cascode amplifier and if you calculate unity gain bandwidth or whatever may be gain bandwidth, this will have more bandwidth than your cascade amplifier. That's what people call this as, when you compare with cascade, this is what is having wide band. Therefore, you can call this as wide band amplifier with respect to cascade amplifier. That is the advantage. But gain is almost same, not exactly same, but almost same. That now let's see problem number 2. Problem number 2. What is that? If the transistor in the figure is in saturation, then this is base, collector, emitter. This is base current. And this is what is having beta DC. Beta DC is nothing but DC current gain. DC current gain. Okay. Then, if this is the case, option A, IC is always equal to beta into IB. Option B, IC is always equal to minus beta into IB. Option C, IC is greater than or equal to beta into IB. Option D, IC is less than or equal to beta into IB. Okay, and saying that the transistor is in saturation. It is in saturation. I think we had seen this. The concept related to this we had seen already, but it is a problem. Let's see what is the answer. Okay, just listen. I think you have this problem with you. Let's see. Saying that the transistor is in saturation. If the transistor is in saturation, asking for the relation between IC to IB. Therefore, this is what your IC and this is what your IB. Remember, if transistor is in active region, right? If transistor is in active region, the first thing is IC is equal to alpha into IE, or I can say your emitter current IE is equal to IC plus IB, and IC is equal to alpha into IE plus ICBO or IC naught, which is approximately, if you neglect the reverse saturation current, your IC will be equal to alpha into IE, and IC is equal to beta into IB plus 1 plus beta into IC naught. This is what we derived, or ICBO. Do not have any confusion. ICBO. Therefore, if I neglect the reverse saturation current path, this will be approximately equal to beta into IB. Remember, this is true, this is true, this is true only when the transistor is in active region. Only when the transistor is in active region. Therefore, if the transistor is in active region, then you can say IC is always equal to beta into IB. IC is always equal to beta into IB. But he is saying that transistor is not in active region. Transistor is in saturation. If transistor is in saturation, all these equations are not valid. Then what is valid? Then which is true? That is what is asking. I guess you understood, right? Now, just listen. I'll tell you a point. If you take common emitter amplifier, let us consider CE configuration. Right? What is that? This is what is your CE configuration. Right? This is your VCC, then RC. This is what is your VCE. I'm just representing DC point of view. And this is what is your collector current IC. And this is what is your base current IB. Okay. And this is what is your VBE. What it may be, we are connecting through something. Okay, let it maybe this is what is your VBB. What it may be, this is your VBB, and this is your RB, and this is what is your VBE. Right? Okay. Now let us say, see, tell me what is the condition for active region or saturation region. Your VBE should be greater than or equal to 0.7. and your VCE should be greater than 0.2. Then the transistor is said to be in active region. Then your IC is equal to beta into IB is valid. Then amplification, because the voltage what you apply, this is a DC condition on top of the DC, because the DC voltages are for biasing the transistor to keep the transistor in active region. Once the transistor is in active region, now it is ready for the amplification with capital IC, capital VC, which is nothing but your operating point at the output. Now the transistor, the circuit is in active region, therefore it is ready for the amplification. Now you can apply the signal what you want to amplify on top of the DC what you have. This is what is equivalent representation. Okay. Then when you put AC source on top of the DC, whatever AC signal you are applying, that is what is converted into your VBE change, that is what is converted into your IB change. The small signal change in the IB will be converted into large signal change in IC, because IC to IB relation is current amplification. Therefore, small signal change in IB is converted into large signal change in IC. Large signal change in IC is nothing but large voltage drop change in RC. Therefore, large voltage change at the output. Therefore, you have more voltage peak to peak with respect to small voltage peak to peak what you apply, we are getting voltage amplification. That is what we discussed already. Right? Now the point is, let us say I am speaking with respect to what? I am speaking with respect to DC condition, not AC condition. Therefore, in DC condition, our job is to keep the transistor in active region. Let us say, for your understanding, I am applying my VBB. Let us say VBB is equal to 2 volt, and then RB is chosen such that IB is something, VBE is 0.7. Let us say this is what is your 0.7 volt, and we got some IC corresponding to RC something. Then let us say your VCE is equal to 5 volt, and this is nothing but greater than 0.2. If this is what is greater than 0.2, therefore transistor is in active region. That's fine. Then IC is equal to beta into IB is valid. IC is equal to beta into IB is valid. It is true because it is in active region. Okay. Let us say I am just giving not 2, something else. Right. Now what I want to do is the same thing. I will try to explain. This is what is your x-axis. Let me say my x-axis is IB and my y-axis is IC. Right? Therefore, let us say I am increasing my IB because I am increasing my VBE. Why? I am increasing my VBB. Let us say I am increasing my VBB. If I increase my VBB DC only, then my VBE will increase by a small value. Then my IB will increase. If IB will increase, surely IC will increase because IC is equal to beta into IB, that is valid under active region. Then your IC will increase. When IC is increasing, then the drop across RC will increase. Therefore, maybe for your understanding, I am just taking VCC is equal to 10 volts. Out of 10, 5 volt is dropped here, remaining 5 volt is coming here. Okay. Therefore, now tell me what will happen if IB is increasing, your IC will increase, drop across RC will increase, then your VCE will decrease, your 5 will become, let us say, 4.5, 4.2. Still that is greater than 0.2, still that is in active region. Therefore, until the transistor is in active region, your IC is equal to beta into IB is valid. Therefore, what does it mean? If I increase my IB, what will happen to IC? Your IC also will increase. If I increase my IB, your IC also will increase with some slope. What is the slope now? The slope is nothing but your beta, y is equal to mx. Y axis is IC, x axis is nothing but your IB. Therefore, y is equal to m into x. The slope is nothing but your beta. That is fine. But now, remember, as I am increasing my VBB, right, then my VBE is increasing, then my IB is increasing, then my IC is increasing, then the drop across RC is increasing. Let us say the drop across RC is close to 10 because I am increasing it continuously. Then my VCE will be decreasing. The moment when VCE is becoming close to 0 or 0.2, then transistor will come out of active region. Then it will enter into saturation. Then remember, maybe I can say this is what is case 1, then case 2, right? Now this is an active region, that is fine. Now case 2, this is what your case 1. Now case 2, I am increasing such that VBE is becoming 0.8 and VCE, that is what is giving you output. Therefore VCE is becoming 0.2, let us say. Then it is not an active region. Remember that IC is equal to beta into IB, right? Is not valid. When the transistor is entering into saturation, then IC is equal to beta into IB is not valid. Then your output side, because VCC is fixed, RC is fixed, right? Transistor now entered into saturation. Till then, till it is not entering into saturation, if it is in active region, then your IC is controlled by IB. Then if IC is changing, the drop across RC is changing, then VCE is changing. Therefore, your output is controlled by indirectly your IB. But now, once the transistor entered into saturation, now IC is not controlled by your IB. Your IC will be controlled by your output parameters. And VCE, when VCE reaches to 0.2, then your IC is independent of IB. Because it came out of active region. When it came out of active region, your IC is independent of IB. IC to IB relation is not there. Your IC is different, your IB will be different. There is no link between IC to IB. There is a link between IC to IB only when the transistor is in active region. That is what is this. Therefore, now tell me what is the case. If I complete the graph, therefore, you are increasing your IB. Let us say this is my IC. Increasing IB, IC is also increasing when the transistor is in active region. Once you cross your IB by something, then your IC is also maximum, your VC is minimum, transistor entered into saturation. Then your IC won't be controlled by your IB. But IB can increase, but your IC cannot increase because the relation between IC to IB is gone. Therefore, by increasing your VBB further and further, even the transistor entered into saturation, your IB can increase because of the loop, input loop. But IB is not controlling your IC. Once the transistor is entering into saturation, then your IC is fixed. It will stay there. Your IB can increase because now these two are independent loops. This is input loop, this is output loop. Therefore, now if I complete, what will happen? Let us say this is what is my, what we call, till this point, let us say, this is what is my saturation point. This is what is our saturation point. Then your IB can increase. IB is increasing, let us say mathematical equation. This is what is beta IB. Your IB increasing, beta into IB is increasing. It is a mathematical factor, beta into IB. But remember, what is your IC? Your IC will be tracking to it till it is entered into saturation. Let us say this is what your saturation point or saturation region. Once the transistor is entering into saturation region, your IC is constant. Your output loop is not having any variable. Therefore, your IC will be constant. This is what is our IC sat. And this is what is our till this point, because this is in active region. Therefore, tell me what is the answer. Now you can say the answer. If transistor is in active region, IC is equal to, your IC is equal to beta into IB. That is what is true. If the transistor is in, this is what is your active region, right? If the transistor is in saturation region, what is your IC? Your IC is less than beta into IB. Remember, both are different. Your IB can increase, but IC will not increase. But your IC is already saturated. Therefore, but beta IB, your IB can increase. Therefore, IC is less than beta into IB. But exactly at the edge where it is coming out of active region and entering into saturation region, that is what your edge. You can say IC is equal to beta into IB, or IC is less than or equal to beta into IB. Therefore, close together. Overall, if you ask me, what is IC? Your IC is less than beta into IB in saturation is equal to beta into IB in active region, but exactly at the edge, it is active region as well as saturation region. End of active region, starting of saturation region. Therefore, there it will be equal, but as you go on, it will be less. Therefore, less than or equal to beta into IB. This is the answer. Okay? Take it. Therefore, what is the answer? Answer is IC is less than or equal to beta into IB. Why there is equal, less than, everybody will understand. But why it is equal? Exactly at the edge, end of active region, starting of saturation region. Okay? Take it. And this is what people call it as IB minimum enter into saturation. Now we can solve problem number 3. Write down problem number 3. In the amplifier circuit shown in figure, the values of R1 and R2 are such that the transistor is operating at VCE is equal to 3 volt, IC is equal to 1.5 milliampere when its beta is 150. For a transistor with beta is equal to 200, the operating point is. Again, this is DC analysis problem. I hope this is done. Okay, fine. Now write down problem number 3. Circuit is given. The circuit is This is R1, R2, VCC 6 volt. Okay. Now the problem is when beta is 150, when beta is 150, then your operating point VCE comma IC is equal to 3 volt comma 1.5 milliampere. Now what is asking, when new beta, let us say beta dash 200, then what is our new VC and new IC? This is what is the problem statement. I just decoded into this way. If you understand clearly, right, then if you ask me what is option A, 2 volt 2 milliampere, option B 3 volt 2 milliampere, option C 4 volt 2 milliampere, option D 4 volt 1 milliampere. The new operating point means new VCE and the new IC. Let me explain the problem once again. See, this is what is your circuit. Actually, tell me, is the problem related to AC analysis or DC analysis? Definitely DC analysis, because asking for operating point, DC voltage and DC current. Therefore, no need to bother about AC components. Therefore, no need to bother about this capacitor here, because this is for AC output, AC input. Therefore, we don't need to bother about AC parameters, only DC. This is what is the circuit. Now, the meaning of this is, let us say you are biasing the circuit or you are biasing the transistor such that you got an operating point of VCE and then IC. VCE is 3, which is greater than 0.2. Transistor is in active region. Fine. Now, due to some reason, your beta or transistor has gone. It has burnt due to some reason. What you do? Take out the transistor, keep one more transistor. Let us say transistor is replaced by another transistor, but now the transistor is not having 150, now it is having 200. What is the beta of the new transistor? That is 200. If that is what is having 200, then what is your new operating point? That is what is the question. I hope this is understood, right? Now let's see. If you consider this as a DC problem, I can say qualitatively we can think about it. Your input side nothing is changed, okay? Then if beta is increasing, your IC will increase. Then the drop across R2 will increase. Your VCE will decrease. IC will be more than 1.5 milliampere. Your VCE will be less than 3 volt. That is the answer. IC will be more than 1.5 milliampere. Option A, option B, option C, all are true. And then VCE will be less than 3 volt. VCE will be less than 3 volt. Actually, option A is correct. No need to solve, but let's solve and then let's see. Okay. Now, case 1, when beta is 150, okay? Case 1, when beta is 150, you can follow me, right? Now, I think you can find what is IB, right? How will you find IB? First of all, you know IC and you know beta, right? Therefore, tell me what is your IB. This is what your IB, and this is what your IC. Right? Therefore, when beta is 150, you can calculate R1 and then R2. This is your VCC, that is what is your 6 volt. This is your VBE, let us say VBE is 0.7 volt. If nothing is given, you can take that way. And this is your R1 and this is what your IB. And this is what you are having IC. What is IC? IC is already given, which is 1.5 milliampere. And what is VCE? VCE is already given, which is nothing but 3 volt. Right? Therefore, now tell me, what is your IB? And it is having beta, which is 150. Therefore, your IC, we know that IC is equal to beta into IB. Then what is your IB? Your IB is equal to IC by beta. What is IC? 1.5 milliampere divided by beta is 150, which is nothing but what? 150 100, which is 10 microampere. Okay, this is fine. Then output KVL to find R2. Actually you can find R1 but it is not required. How will you find R1? Input KVL. Input KVL VCC is equal to IB into R1 plus VBE. You know VCC, you know VBE, you know IB, and you can find R1. But it is not required because even if you change your transistor to new transistor, its VBE is constant, then your R1 is constant, but your IB is also constant. That's why this is required for me. Therefore, this is what your IB. Now tell me to find R2. To find R2. What is the R2? Output KVL. If you apply output KVL, what is that? VCC is equal to this voltage is equal to this voltage plus this voltage, which is nothing but IC into R2 plus VCE. Then tell me what your R2? Your R2 will be equal to VCC minus, what is VCC? 6 minus VCE, it's already given 3 divided by IC. What is IC? 1.5 milliampere. Therefore 6 minus 3, 3 by 1.5, 2, milli will become K. Therefore what is the R2? R2 will be 2 kilo ohm. Therefore what is R2? R2 is 2 kilo ohm. That's what we got. Now case 2, new transistor which is having beta 200. Now your beta is updated. Now beta is not 150, now beta is 200. Then what is your new operating system? Your transistor is replaced by another transistor which is having beta 200. Then this is your beta dash. Your R1, R2 won't change. R2 is already known to you, which is 2K. You can calculate R1 also, but it is not required because ultimately IB is important. IB is 10 microampere. That is not changed. That won't change, right? Because VB is almost 0.7. Then this is your VCC, which is equal to 6 volt. Now you will get new collector current IC dash. You will get new collector to emitter voltage VC dash. That is what. Therefore now tell me what is your IC dash? Therefore IC dash is equal to new beta dash into IB. Your IB is not changing. Beta dash is nothing but 200 into 10 micro, which is nothing but 2000 micro ampere, which is basically 2 milliampere. IC dash is done. Now to find VCE dash. Therefore what is VCE dash? From output KVL. VCC minus, out of this voltage, if you take out the drop across R2, that is VCE dash. VCC minus new IC dash into R2. What is VCC? 6 minus IC dash 2 milliampere into 2K. K and then milli will become, it will be 1, then it will be 2 volt. Therefore, what is your new operating point? VCE dash comma IC dash is equal to 2 volt comma 2 milliampere. Still the transistor is in active region. Okay. Therefore, what is the answer? The answer is A. I hope everyone understood the procedure. Okay. Therefore, if the transistor beta is changing, your operating point will change. And we know that even though transistor is not replaced, if temperature changes, your beta changes. If beta changes, your Q point changes. That's why this circuit is not having any operating point stability. Your operating point is not stable. Remember, if temperature changes, your beta changes. If beta changes, your Q point is changing. That's why this is what is called fixed bias circuit. That's why we went to self bias circuit or collector to base bias circuit to provide Q point stability. That we studied already. Okay. Take it. Now I think we cannot solve next problem in this session. We will continue in the next session, right? By the time you copy this and you try to solve on your own. If you are not able to get, then only you see the solution on the board. Okay, till then, fine. We will meet in the next session for the problem number 4. Okay, thank you.